Hello everyone, welcome to week 6 of HSCI 6263. So far, we have majorly looked at several statistical methods when there is only one independent variable that's nominal or numerical or ordinal in nature. And now we know very well that the choice of statistical methods depends on the research question, the scales on which the variables are measured, and the number of variables to be analyzed. This week, we will look at statistical procedures where there are more than one dependent or independent variables. In general, such statistical procedures are called multivariate analysis. This week covers various multivariate analysis techniques like multiple linear regression, which is an extension of simple linear regression when there are more than one predictor variables. Last week, we looked at simple linear regression, which is a model that has only one predictor variable. And general linear models, or they're simply a lot of times called GLMs, are an extension of multiple regression. Multiple regression only looks at one dependent variable, whereas general linear model allows us to analyze several dependent variables in a linear combination. The tests that we have looked at in the previous sections, like ANOVA, t-test, f-test, and etc., are also forms of general linear models. ANCOVA is another multivariate analysis technique. It's called analysis of covariance. It's an extension of ANOVA in which the main effects and interactions are assessed on the dependent variable scores after the dependent variable has been adjusted for the dependent variable's relationship with one or more covariates or confounding variables. Logistic regression is a method that's commonly used when the dependent variable includes both the numerical and nominal measures, and the outcome variable is binary or dichotomous. The details of these statistical methods or multivariate analysis methods are included in the archived lectures or supplemental videos for this week. So please watch those videos as they provide the basic concepts for these subtopics. And I just quickly want to mention about MANOVA, which is an extension of ANOVA, in which main effects and interactions are assessed on a combination of dependent variables. It's a method used to perform an ANOVA-style analysis on several independent variables simultaneously. We usually do MANOVA instead of a series of one at a time ANOVAs for two main reasons. The first one is it is to reduce the experiment-wise level of type 1 error, and the second reason is to assess if the combination of dependent variables produce significant main effect. There are times that none of the individual ANOVAs may produce a significant main effect on the dependent variable, but in combination, they might provide significant main effect, which suggests that the variables are more meaningful when taken together than considered separately. I will go over Cox regression next week along with our topic survival analysis, and on the subsequent few slides I would spend some time on the discussion of meta-analysis. Meta-analysis is different from the methods discussed on the previous sections. You, as a consumer of statistics, will review articles for different studies in the medical literature. Meta-analysis provides ways to contrast and combine the results from several previous studies in the literature dealing with related topic in a statistical and quantitative way, in the hope of establishing a conclusion on quantifiable or defendable patterns. Meta-analysis is conducted to achieve a better understanding of a research data and to achieve more precise and accurate estimates and to achieve higher power of the measure of interest to generate new hypotheses, to examine subgroups with individual numbers that are not statistically significant. And among the many things, the one basic thing that we do meta-analysis for is to get a better estimate of the statistic of interest. These are the basic steps for meta-analysis. We first identify the research problem and we do a search in the literature, and based on the findings from the literature, we select the studies that we are interested in that are really related with our research problem. And we identify our dependent and independent variables. And then we do selection of a statistical method to perform our analysis. And then we would actually perform the meta-analysis. And then we would interpret the results and draw conclusions on the meta-analysis. Meta-analysis is useful when we have more than one study that has measured an effect, and when studies are sufficiently similar to produce a meaningful and useful result, and when the outcome of interest have been measured in similar ways, and the results of the studies have been inconsistent. So basically, meta-analysis, as we said before, is combining the results from different similar studies. So we can only do meta-analysis when we have studies that are sufficiently similar and they have an outcome of interest that has been measured in very similar ways. The advantages of meta-analysis are first, it gives a greater statistical power than just individual studies. And it's also useful to confirm results of individual data analysis. And it's used as a confirmatory data analysis. It is an evidence-based resource. And it is a cheaper way of research as there is no need for a clinical trial cost. Basically, it's based upon the data from the literature findings. And there are also some disadvantages of meta-analysis, including the difficulty and the fact that it's really a time-consuming procedure to identify the appropriate studies that have our outcome of interest. And also, not all studies provide adequate data for the inclusion and analysis. And also, meta-analysis is subject to publication bias. Publication bias is a term for what occurs when the research that appears in the published literature is systematically unrepresentative of the population of the completed studies, because a lot of times people tend to present the good findings from their studies into the literature. And meta-analysis may also require more and advanced statistical methods than analyzing an ordinary study data. And also, it also has heterogeneity of the study populations because it's from data from very different studies. Meta-analysis results are presented in a beautiful plot that's called forest plot. It is not what you think. It doesn't really look like a forest at all, but actually looks like this. Forest plot has a bunch of confidence intervals from the different studies or the different literature findings that we have found in our literature search. This is an example forest plot. And then in the next few slides, I would go over a simple example of one meta-analysis. Here's an example of a meta-analysis by Rampura, Hipani, and Wu, published in JAMA back in 2011. This was done to assess treatment-related mortality with bevacizumab in cancer patients. And the researchers wanted to determine the overall risk of fatal adverse events associated with bevacizumab. When they did the meta-analysis, they searched for literatures on various databases like PubMed, Embase, and Web of Science. And they looked at literatures that have the data for the fatal adverse events of bevacizumab from January 1966 to October 2010. The eligible studies for this meta-analysis were randomized and controlled trials in which bevacizumab in combination with chemotherapy or biological therapy was compared with chemotherapy or biological therapy alone. And they wanted to analyze the data using incidence rates, relative risks, and the associated 95% confidence intervals for the relative risks. The relative risk is calculated by dividing the proportion of fatal adverse events in the bevacizumab group divided by the fatal adverse events in the chemotherapy group. So if the relative risk is 1, then we can conclude that bevacizumab and chemotherapy are equally likely to have fatal adverse events. And if the relative risk is greater than 1, then it could be concluded that bevacizumab is more likely to have fatal adverse events than chemotherapy. And if the relative risk is less than 1, then we can conclude that bevacizumab is less likely to have fatal adverse events than chemotherapy. The researchers, based on their database search, have identified 385 publications, and of which they have excluded 347 of them because of several reasons. And then they selected 42 randomized controlled trials of bevacizumab therapy. And from these 42 trials, 26 of them were excluded because 17 of them, both the control and treatment groups, receive bevacizumab, and 9 of them data does not include adequate evaluation of the fatal adverse events. So the meta-analysis focused on 16 randomized controlled trials, of which 4 of them are from phase 2 clinical trials and 12 of them were from phase 3 clinical trials. As you see, you can imagine how time consuming it would be to look at 385 publications and assess if each and every one of them are literature findings that you want to use for your meta-analysis or not. From the 16 randomizing control trials, there were a total of 10,217 patients with variety of solid tumors. And the overall incidence of fatal adverse events in the bevacizumab group was found out to be 2.9%, whereas in the chemotherapy alone group was 1.96%. When after calculating the relative risk, we found out that bevacizumab was associated with an increased risk of fatal SAEs. The relative risk from this data or from this meta-analysis was 1.33% with a 95% confidence interval ranging from 1.02 to 1.73. And the conclusion from this meta-analysis is that in a meta-analysis of randomized controlled trials, bevacizumab in combination with chemotherapy or biological therapy compared with chemotherapy alone was associated with an increased treatment-related mortality or fatal adverse events. This for this week. I hope you have a great week, and as you work on your journal assignment for this week, please let me know if you have questions, and I should be able to help. Good luck.